The material wealth of a nation springs from the earth, from the minerals within the earth, from the vegetation which grows out of the earth, and from the animals which thrive on the produce of the earth and provide us with so much of our essential food and clothing. In natural resources, the United States of America is commonly regarded as one of the wealthiest nations on the face of the globe. Before the war, we had more than enough of iron and steel with which to fabricate our manufactured products, more than enough of wheat, so that bread was plentiful and we could ship our excess crops to foreign lands, more than enough of cotton, and for that matter, more than enough of many other raw materials required to provide us with the needs and comforts of a peacetime life. In a number of materials, however, we were woefully deficient and were forced to go overseas for our requirements. The most critical of these deficiencies was rubber. We rode on rubber, used it in thousands of different shapes and forms, and we took it very much for granted. Yet more than 95% of this rubber came not from the United States, but from rubber plantations in Malaya and the Dutch East Indies, halfway round the globe. Singapore was an important city in the rubber trade, but not all the rubber that originated in the Far East was controlled by the British or the Dutch. To the contrary, over a period of many years, a number of American manufacturers had been taking vigorous steps to protect their sources of supply. In the course of this development, the United States Rubber Company, with extensive holdings in the Far East, became the largest single producer of natural rubber in the world. Yet even so, it still had to look to foreign-owned plantations for fully 85% of its total requirements of rubber. Suddenly came a series of events which completely changed the picture. In the early months of 1942, we found ourselves cut off from our greatest source of natural rubber, and we were at war. For many years, the discovery of a substitute for natural rubber had been one of the great dreams of organic chemistry. And long before our supply of natural rubber was cut off, much of the pioneering in synthetic rubbers had already been done. At Naugatuck, Connecticut, where one of the first of the government plants was built, the United States Rubber Company, more than a year before Pearl Harbor, was already making a rubber known as Buna S in one of the country's earliest pilot plants. The coming of war, with America's sources of natural rubber almost entirely cut off, now made it necessary to produce synthetic rubber in great quantities. For of all critical and strategic materials, in the words of the Baruch report, rubber was the one which presented the greatest threat to the safety of the nation and the success of the Allied cause. One type alone of the 5 different types of synthetic rubber offered greatest hope for the prompt meeting of America's wartime needs. This type was Buna S, or GRS, government rubber styrene type, and nearly 90% of the government's program was therefore centered on its production. There were 3 reasons for this choice. First, Buna S could be derived in large part either from crude oil, which was readily available in large quantities, or from alcohol, distilled from various grains, wheat, barley, rye, corn, and the like, which America already grew in abundance. Second, while the building and equipping of the needed plants for the mass production of Buna S was a tremendous project, they could be built and put in operation before America's stockpile of rubber was exhausted. Third, at a time when all manufacturing facilities were strained to the utmost, Buna S could be made into essential military products in existing rubber plants. What is Buna S? It bounces, it stretches, and the stretched portion, when released, immediately flies back to its original position. What actually is its chemical composition? To begin with, it belongs to the great family of hydrocarbons, of which the simplest in chemical structure is a gas called methane. the principal constituent of natural gas, which is here seen burning in the Texas oil fields. When, in nature, an atom of carbon has 4 atoms of hydrogen attached to it, the result is a molecule of methane gas. The atoms of hydrogen spin round the central atoms of carbon like little satellites. They are held in their orbits by forces known as valences. Note that each carbon atom has a valence of 4. It can combine with 4 other atoms, but no more. Carbon, more than any other element, has the power of combining with itself to form either rings or chains. Here is a chain of 2 carbon atoms. If all the free valences were occupied by atoms of hydrogen, we have a single molecule of a gas called ethane, which is chemically related to alcohol. Extend the chain to include 3 carbon atoms, and we have a single molecule of a gas called propane, which is one of the constituents of bottled gas used in rural communities. Extend it further to include 4 carbon atoms, and we have a single molecule of a gas called butane, another constituent of natural gas. And now let us change the pattern slightly by throwing out 4 atoms of hydrogen and doubling up on 2 of the valences. We now have a gas called butadiene. Change it again, but in only one particular, and we have a single molecule of a liquid known as isoprene. Suppose now this chain attracts a second, and a third, and that they are now joined by hundreds, even thousands of others, all strung together in a series. The result is a giant molecule, or polymer, as the chemists say, and its name is rubber. Incidentally, the hooking up of these molecules is known as polymerization. If we now can imagine thousands, even millions of these molecules all hooked together and interlaced with one another, we can possibly get a very rough idea of the structure of natural rubber. But in the case of natural rubber, sad to say, this polymerization occurs only in nature. It has never been duplicated in a laboratory. Just as natural rubber has its molecular basis, isoprene, so Buna S synthetic rubber has its molecular basis, and it's very similar. In place of isoprene, the chemists start with the hydrocarbon butadiene, and they hook it up with a second hydrocarbon known as styrene. Incidentally, the hexagon is used to symbolize the well-known benzene ring. If you will now imagine a series of these units strung together to form a giant molecule, you will have a symbolic picture of the type of synthetic rubber known as Buna S. Of all the synthetics, Buna S is most similar to natural rubber in processing and performance characteristics. It was selected, as we have said, to meet the greater part of America's wartime needs for rubber. And in little more than 2 years from Pearl Harbor, our fabulous American synthetic rubber industry had achieved a production greater than the pre-war consumption of rubber for all purposes. Here is the first of the great integrated standard plants of the government's rubber program to come into production. The plant at Institute, West Virginia. The Institute plant, together with other plants in the government's gigantic program, were financed by the Defense Plant Corporation. They are operated for and under the direction of the Rubber Reserve Company. Butadiene, which accounts for 3/4 of the weight of finished Buna S synthetic rubber, is a gas at ordinary temperatures. It is made from alcohol at an adjacent plant and conveyed by pipeline under pressure to these butadiene storage tanks. Styrene, which will later be hooked up with butadiene, is a liquid and it too is made at an adjacent plant and is piped for storage to this tank farm. Other chemicals, though in smaller quantities, are used in making Buna S. One of these is soap. The soap chips are sifted through a screen and float down into the weighing hopper on the floor below. The operator runs purified water into the tanks, then releases precisely the right amount of soap as determined by weight. The mixture is stirred till the soap dissolves. Meanwhile, other ingredients are added. One of these ingredients, known as a catalyst, has a very special job to perform. While it never combines with the other chemicals and never appears in the finished rubber, it controls the speed of the reaction. It is a big factor in making possible our huge present-day production of synthetic rubber. After the soap solution is prepared, it is piped to large tanks, from which it will later be forced by this battery of pumps into the reactors, where the actual polymerization takes place. The clear butadiene and the styrene are now pumped from the storage tanks through a maze of pipes, and purified water is added. Then, in measured quantities, they are pumped into a reactor, together with the soap solution and purified water. By agitation, the hydrocarbons, butadiene and styrene, are now beaten up into fine droplets to form an emulsion, just as oil is whipped up in a salad dressing. When the ingredients have been thoroughly mixed, warm water is conducted to the outer jackets of the reactors to warm up the batch and start the cooking process. In these banks of recording meters, a continuous record is kept of the temperature and pressure in each vessel. This is essential because the polymerization gives off heat. The huge cooling tower shown here removes heat from the cooling water so that the water may be used over again. The water is pumped to the top of the tower. These large fans assist in the cooling process. Materials are checked by sampling. A closed bomb is necessary to prevent loss of the volatile butadiene. To control all phases of both raw materials and finished product, nearly 1,800 samples at all stages of the process are checked and tested every day by more than 100 chemists and analysts. As polymerization occurs, rubber is formed in the emulsified solutions. The resulting mixture is called latex. Actually, the latex consists of minute particles of rubber suspended in water. Our next job is to coagulate these particles. Two substances are used for this purpose: sulfuric acid of special concentration previously prepared and stored in tanks, and a solution of rock salt which has previously been prepared and purified. These two ingredients convert the minute particles of rubber to the form of flocks or crumbs large enough to be screened off. The latex flows into a creaming tank where it is mixed with pure salt solution. This solution causes a thickening of the latex, but it does more. It controls the size of the coagulated particles and prevents the rubber from gathering into large chunks, which would be difficult to handle. As the mixture is stirred, a dilute solution of sulfuric acid is fed in. This causes the tiny particles of rubber to form into larger lumps, which, as you see, can be readily separated from the liquid. When all the tiny particles have coagulated and no rubber remains that could be lost in subsequent washing operations, this slurry is allowed to flow to a second tank, where more acid is added to convert the excess soap and permit it to be readily removed. There now remains only the acid to get rid of, and its removal is accomplished by washing on a continuous rotary vacuum filter. The rubber is here washed and squeezed to remove all surface water. The bits of rubber cling to one another to form a thick blanket. The blanket of rubber is removed from the filter by a revolving doctor blade, which, as it turns, picks the rubber from the filter and tears the sheet into fragments. The broken slabs now travel by conveyor belt to the final drying operation. These walls on either side are the walls of 2 of the 12 enormous dryers. As the rubber passes through the dryer and the water is removed, the bits of rubber adhere together again. Here we see the resultant mass being broken into pieces which can be handled readily. The dried rubber is carried by conveyor to the hopper of a baling press, where 75-pound lots of dry crumb are weighed out and dropped into the baling chamber. And now suppose we review the process step by step. Starting with either crude oil or alcohol, we get the hydrocarbon butadiene. Starting with coal tar and petroleum, we get the hydrocarbon styrene. Our task is to polymerize these 2 hydrocarbons, and this is accomplished in a huge tank known as a reactor. A soap solution is piped into the reactor, where the hydrocarbons are beaten into fine droplets. Here also heat is applied, and minute particles of rubber, known as latex, form in the emulsified solution. The latex is piped to a series of tanks. Where a salt solution and sulfuric acid help to coagulate the particles. The rubber now goes to a rotary filter, where it is washed, squeezed, broken into fragments, and conveyed to the dryers. The dry crumbs now travel by conveyor to the baling press. Spurred by wartime needs, the production of Buna S in tremendous volume represents an achievement of which every American may well be proud. Many of the details are still a closely guarded secret, but when the full story of synthetic rubber is told, it will pay thrilling tribute to the research chemists of the United States Rubber Company. It will tell, for example, of a secret chemical coded OEI, which controls the growth and structure of the chain molecules, and thus makes a rubber which is easier to process. And it will tell of other important discoveries, tested in the battle zones on land, on sea, and in the air, which will open to a peacetime world an array of synthetic rubber products which in some ways will even surpass their pre-war counterparts. Consider the synthetic rubber footwear of the future, for example. What tougher proving ground could be provided than the mud of the invasion areas or the jungles of New Guinea? Again, what greater proof of the watertight and airtight qualities of synthetic rubber than has already been established through the successful use of attack boats such as these? The war has been a grim master. Now it may call for a rubber-lined fuel tank, so cunningly contrived that even though pierced by machine gun bullets, the rubber seals the punctures. Or again, it may call for huge pontons to make possible the swift crossing of a river. Or again, it may call for barrage balloons to serve as convoys for our moving troops, our ships at sea. Not yet can its flood of wartime goods be diverted into peacetime channels. When the day of conversion comes, there is already much new knowledge, born of intensive searchings in the realm of synthetic rubbers, that will quickly be enlisted by the chemists of United States Rubber Company. Serving through science, they are already helping to provide new and better things of rubber in the interest of all people everywhere throughout the globe.